Good afternoon, everybody. It's my pleasure to now introduce you to Dr. Corsin Battaglia, who's from Empa, and is going to give us a presentation on interface stability in all solid-state batteries. As usual, please leave your questions in the sidebar, and we'll take these at the end of the presentation. And I'm now going to hand over to Corsin.
Great. So good afternoon from my side, and thank you, Chris, for the introduction, and also to the entire TechBlick team for organizing this event. We just had a great introduction from Shalu on solid-state batteries and what are the different players in the field, and also what type of materials they're working on. And from my side, I'm working at Empa. It's a Swiss Federal Laboratories for Material Science and Technology. So we are material scientists. And what I want to give you today is a bit of a flavor, where the current challenges lie. And there's a lot of expectation for solid-state batteries, and I think this comes mainly from the fact that most of the components are already available, but to make them work together is still relatively challenging, and so we'll discuss today some of the challenges related to interface stability between these components. So in my lab, we're working on a number of different battery technologies, so basically next generation lithium-ion batteries with liquid electrolytes, carbonate-based electrolytes, but also we're trying to make electrolytes more sustainable, so we work on aqueous system, also on ionic liquid-based electrolytes. And then the second part here on a different number of solid electrolytes. And in my lab, we are not working on the sulfide electrolytes. Shalu pointed out before, this is basically many companies are working in this field. And indeed, it's also a relatively crowded space already in terms of IP. So we have chosen some more niche materials, which I'm going to present to you today. We work on polymer, oxides, and hydroborates. And you see on the left side, you have a different number or a series of different cathode materials that we're working on in our lab, which are also all available to be integrated in a solid-state batteries. Whereas on the right side, I think this is really where we are focusing on, that we're trying to integrate lithium metal or also sodium metal anodes into solid-state batteries. Because I think it's very important to understand that solid-state batteries don't just automatically provide higher energy density than the current state-of-the-art lithium-ion batteries with liquid electrolytes, that the key is really the enabler to go to higher energy density is to integrate either a lithium or a sodium metal anode. And so we have a lot of collaborations also with industry, not just on solid-state batteries, but also on liquid electrolyte-based batteries. But many of these projects, we are actually working very closely also with industrial partners. My lab is also coordinating a large European project. It's the project SENSE, where we're working on the next generation, not solid-state, but still with liquid electrolyte batteries. But we are working on safe electrolytes, so it's also possible for example, to make non-flammable electrolytes for lithium-ion batteries. And see, we have also a number of partners here, including also the cell manufacturers FAM in Italy and Northvolt in Sweden. Okay, but coming back to the overview slide, so today I want to give you a bit of flavor on oxide electrolytes, what we've been working on in recent years, and also on hydroborate electrolytes. I think we are really one of the let's say it's a special class of material where there are not so many people that are working on. We've been working on these materials now for 6 to 7 years already, and we have been keeping the pace relatively at the same level like with the sulfur-based electrolytes. I'll just give you an introduction on those type of materials. Okay, so oxides as solid electrolytes, I think they are in particularly heavily investigated because they are also compatible with lithium and sodium metal anodes. And in this study in particular, we try to understand what is the critical current density for dendrite formation. You know that lithium and sodium metal anodes are considered a holy grail in the battery community because basically if you replace a graphite anode, for example, with a lithium metal anode, the energy density of your battery would almost increase by a factor of 2 roughly. And so the big challenge is that we have dendrites that can form, so basically that can short the cell between the anode and the cathode. So in the worst case, the battery can go into thermal runaway and then explode. And this can also happen, in the solid-state batteries. It's very important to understand that kind of behavior. So what we showed in this study is that basically we looked at the critical current density as a function of temperature for lithium metal in contact with lithium